Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So today's speaker is Sergei Foaming. Sergei graduated from St. Petersburg, went to MIT. I took a class from him there. And then he went to the University of Michigan, where with Andrei Zolovinsky, they developed cluster algebras. And so this is a reprise of his talk at the International Congress of Mathematicians.
Thank you, David. Thank you all for coming here. This is probably more algebraic than this audience is used to, so my apologies for that. Well, this talk is a kind of lightning speed introduction into cluster algebras, but you can slow me down and ask questions and ask to explain things more concretely, but this would be at the expense of making the talk longer. so just be aware of that. Okay. So if you, it's based on joint work with various people listed here, both alphabetically and in increasing order of their contributions. We discovered cluster algebras with Andrei and developed this theory quite a bit. Partly together with Arkady Berenstein from Oregon, and then there was follow-up work with Michael Shapiro and Dylan Thurston on cluster algebras associated with triangulated surfaces. This will come at the end of the talk. I don't know if I will actually have time to discuss it in much detail. The slides for my talk are available online, and also there is a full version of this talk on the archive and also in the ICM proceedings. There are a few related talks which discuss other aspects of the subject, because today I will only be able to just scratch the surface. There is, if you prefer the French version, there is a Séminaire Bourbaki talk by Bernhard Keller. Algebra massée is exactly cluster algebras. If you prefer a 15-hour-long version, it's available online also in video format. I gave a master class in June, essentially with the same content, but it took 15 hours. And then there were two other talks at the ICM dealing with more algebraic aspects of the theory, including Idun Reitan's Eminator lecture in cluster categories. The main references are listed in this slide, well, you can find proofs there and more examples. So what are these algebras? It's a class of commutative rings, although there is actually a non-commutative quantum version of them. And they are equipped with a particular kind of combinatorial scaffolding inside. So it's not just a ring, but it's a ring with some distinguished generators and certain relations of a particular kind, which I will try to explain. And it all grew out of George Lustig's work. It was motivated by his work, although he never did anything on this particular subject per se, but it grew out of two seminal developments due to him, his theory of total positivity in semi-simple groups, and his theory of canonical basis. So we were trying to understand those fairly abstract theories and on a more concrete combinatorial level, and this is how the subject came about. So Since then, these types of structures, combinatorial structures, have been identified in a number of contexts, some of which are listed here, and there are many more which I do not list. And you can get a general feeling for how big the subject grew over the last 10 years since we discovered these algebras by visiting a cluster algebras portal, which I maintain. And then there are lots of links there to various papers, seminars, conferences, and so forth. You just Google me, and then there is a link to this portal at the bottom. There will be a special program at MSRI in the fall of 2012 under the name of Cluster Algebras. Now, total positivity, what is that? So total positivity is really one of my most favorite subjects in mathematics. It's not a subfield of mathematics. It's just kind of a phenomenon that occurs throughout various disciplines. And what I like about it is that it sort of bridges between algebra and analysis. So most people, either think as algebraists, basically, or as analysts, even if they pretend to be like in combinatorics or probability, some other field. But there is actually a sort of almost religious division. It's almost like a left and right brain or something between people who are basically at heart algebraists and people who are basically at heart analysts. And the late Vladimir Arnold would characterize this division by saying that algebraists, they prove identities and analysts prove inequalities. And well, that's kind of, he then went on to denigrate the algebraists, but essentially there is some truth to this division. And so what total positivity captures, it captures a class of inequalities which are at the same time algebraic in nature. So even though it deals with sort of analytic aspects in that, we talk about positivity, so obviously inequalities are involved, but the nature of these inequalities is very, very algebraic. So the classical example is totally positive matrices, where you just you declare a matrix TP totally positive if all its minors, that is determinants of square submatrices, are positive real numbers. And a priori, of course, if this is the first time you heard about such matrices, you don't even know that they exist. If there are like 100, if it's a 100 by 100 matrix, there will be exponentially many minors, and maybe these inequalities, when you take them together, right? Because you take any subset of rows and equinumerous subset of columns, maybe these inequalities contradict each other, or maybe, right? Maybe. But not only do such matrices exist, they actually are widespread. They come in a variety of contexts. Initially, they arose in the work of Gantmacher and Crane and Isai Schoenberg on oscillations in mechanical systems and in approximation theory, study of Chebyshev systems. Then there was a crucial discovery by Cardin and McGregor that transition matrices for one-dimensional diffusion processes are TP. And around the same time, Adrien and Thomas discovered an important connection with asymptotic representation theory, more specifically with representations of infinite symmetric groups. Another context in which total positivity comes up is enumerative combinatorics, theory of lattice paths, and very much related appearance in discrete potential theory, planar electric networks and such. And most recently, of course, this work of Lustigs and our follow-up that I already mentioned. So this concept, this notion of total positivity can be generalized from matrices to broader contexts. Basically, if you have an algebraic variety, something given by algebraic equations, you can identify some important functions on that variety, some polynomial, local, regular functions locally given by polynomials. You want those functions, which play the role of minors on GLN, you want them to be positive in order for the point on your variety qualify as a positive point. So which functions exactly you want to look at is unclear. Which varieties have such a structure is unclear. And what I am telling you, this is kind of a piece of just my worldview, is that these cluster algebras, or rather, the varieties for which they are coordinate rings, are sort of natural class of, it's a natural setting for this notion. So I won't talk much about other examples like Grassmannians and other Lie groups, but just have it, you can have it in the back of your mind. So why should we be interested in studying these kinds of totally positive varieties? One reason is that some of them can be identified with important spaces. For example, some spaces naturally arising in Teichmuller theory, they can be viewed in a very, very natural way as sets of positive points of some algebraic variety. So basically, you have some algebraic structure, but it's not an algebraic variety because you are only looking at positive points. Because, well, the nature of your geometric, topological, analytic, whatever problem is such that those quantities should be positive real numbers. Another reason is that passing from a complex variety to its positive part is a first step towards a further degeneration called tropicalization, which I won't talk about, but you heard this buzzword before. It's actually, I'm not making it up here. Yeah. And the third reason is that, strange as it may sound, the set of positive points actually retains a lot of information about the ambient variety as a whole. In fact, it reveals some information which you don't see in the varieties. So here is an example. So here I'm taking totally non-negative, meaning minors are non-negative, upper triangular unipotent matrices. Okay, so you take, well, in this case, 3 by 3 matrices. One's on the diagonal 0, under the diagonal x, y, z above, and you want all the minors to be non-negative. Okay, this is some semi-algebraic set, if you want, given in 3-dimensional space by these inequalities. So you take that space, that set, it has some curved pieces of boundary and some flat pieces of boundary. Any semi-algebraic set has a canonical algebraic stratification. There are pieces of the boundary which are, locally smooth, right? So you look at these pieces, and then there are like edges and vertices and so forth, right? So you get some stratification. And you see how that stratification, so it's basically a stratification by the vanishing pattern here, right? Like which of these inequalities are strict and which are just identities, right? And this creates a structure of a, stratified space, or in this case, cell complex, more or less. And these edges here show attachments to these cells, right? So small dimensional cell is where everything is equal 0, and then stuff starts getting further and further relaxed. And you discover that you discover something called the Brugha order. So it turns out, and this is actually true not just for 3 by 3, but any size, and not just for the unipotent radical in GLN and SLN, but for any semi-simple complex Lie group, that just by looking at the structure of the boundary of that space, of course you need to explain what totally positive means in those contexts, you recover this notion of the Brouillard order, and which is of course important for the understanding of the group. So somehow it's not just, and these are actually sort of Brouillard cells, you know, the intersections of Brouillard cells with the totally non-negative part. So it's somehow, you know, more is revealed rather than less by looking at the non-negative points of a variety.
So just to slow you down, the x at the top should have been x sub greater than or equal to 0. Is that right?
This is capital X. This just means the whole thing. This x. This x means no restrictions. You know, just empty. I mean, but this would have been misleading.
But you could have put x sub greater than or equal to 0, right?
It's the positive part of it.
Oh, right, yes. Well, I don't put those inequalities here, so yeah.
Oh, okay.
So, but yes, right. Yeah, it should be x greater than or equal to 0. Yes,
yeah,
correct.
plus you did.
Correct. Yeah. But you, yes. Mm-hmm. I'm glad you're following. Yeah. Thank you. Mm-hmm. Okay, so like I said, one wonders which algebraic varieties have this kind of notion and which families of regular functions we should consider in defining it. And that's how cluster algebras come about. That's one way of selling them or of pitching them. Okay, here is a prototypical example, which is one of the classical invariant rings. So let's consider the algebra of invariants under the natural action of this upper triangular unipotent group on SLNC. Okay, so what is that? So, well, in this example, we're looking at 4 by n is 4. So you take 4 by 4 matrices of indeterminates, and they satisfy just one equation, which is the determinant is 1, right? Because it's a special linear group. Okay? And then you take polynomials in these 16 variables, but not just any polynomial. You want that polynomial to be invariant under multiplying on the left by any upper triangular unipotent matrix, which is the same as doing row transformations in which you are allowed to add to a row a linear combination of previous rows. Any, right? The row itself gets multiplied by 1 because you get 1, right? So if you think about it, you will realize that any minor of this kind, which occupies certain collection of rows and the first several columns. Oh, sorry. Did I say rows? I should have said columns.
On the previous slide, you actually were multiplying on the right.
Was I? Okay, maybe that's right. On the right. Okay, so then that means columns, right? Because when you do on the left, you deal with columns. Okay, so if you add to a column a linear combination of previous columns. So if your minor occupies the first several columns in any subset of rows, then that minor is not going to change under that kind of elementary transformation. Okay, so it's an element of that ring of invariants, and in fact, the first fundamental theorem of invariant theory tells us that all of them are generated by these minors. In other words, you know, each of them can be expressed as a polynomial in these minors. And they satisfy well-known homogeneous quadratic identities called the Grassmann-Plücke relations. And so these are our God-given functions on that quotient space, which we will want to be positive in order for a point to be totally positive, right? So we are looking at the quotient of G mod n, and we call a point there positive, right? If all these minors are positive. So you represent this point by a matrix X, but really it's a coset modular n, right?
So what's capital N?
Capital N is this upper triangular unipotent matrices, right? So points here are represented just by matrices in G, but when you change that, when you multiply on the right by a matrix in N, none of those quantities change, right? So in reality, they are functions on G mod N, and we call such a coset a totally positive point, and if those functions are positive. Okay? So we can talk about a matrix, but really it doesn't. The matrices which differ by those elementary transformations should be viewed as the same, because we cannot distinguish between them when we. Am I explaining too much? Yeah, sorry. Apologies to algebras in the audience. Okay, so there are this many, roughly speaking, 2 to the n of these minors, right? I mean, we don't take the empty one and the whole thing because it's 1, but everything else is fair game. So there are exponentially many of them, and one would have to test all of them in order to determine whether a particular matrix represents a positive point. But in fact, you don't have to. It's enough to just test this many flag minors. Okay? Why? Let me explain that. So that will require some combinatorics. So let's talk about something called pseudo-line arrangements. A pseudo-line arrangement is something that looks like this. Okay? They are basically like straight lines, right? In that any 2 of them intersect exactly once. Okay, so you take any 2 of these lines, they intersect exactly once, and they run from left edge to the right edge. They are sort of like graphs of continuous functions, and intersect transversally and so forth. No funny business. So and we consider everything just modular isotopy. So we only care about the topology of the picture. Okay, like who goes above what, right? And just in case you wonder, not any such arrangement can be straightened. So not any of them can be deformed continuously to without changing its topological type to an arrangement of straight lines. This has to do with existence of non-realizable matroids, oriented matroids. Okay. So for each such arrangement, we introduce a collection of what's called chamber minors. So what are chamber minors? So you take a chamber of the arrangement, just a region into which the plane is cut by these pseudo-lines, and you look at which lines pass below that chamber. Okay, so in this case, for this chamber, there are 2 of these lines, this one and this one. And the lines are numbered from 1, 2, 3, 4 at the left edge, and 4, 3, 2, 1 at the right edge. Because remember, each line intersects each other. So the order, of course, is going to be completely changed as you move from the left to the right. So, okay. So then we get these chamber minors. Okay, that's hopefully clear. Now let me introduce something I call cluster jargon, because this is I will start calling these things some other names in anticipation of a more general setup. So the chamber minors at the edges, for these particular chambers are called frozen, and the reason is they're not going anywhere as we change the arrangement. So if we start changing the arrangement by making these Yang-Baxter moves, by moving one pseudo-line through intersection of 2 others, these are called flips, right? The arrangement is going to change, but only the interior, the sort of inside, the intermediate part, this part. But on the sides, of course, it will always be the same, right? The set of lines going below this chamber is always going to be numbered by this, 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 and that. Okay? Yes?
So sorry, just to check the meaning of the word variable now. Is it a set of one of these sets of numbers? Right? Go on.
No.
Delta.
A variable is a function on our future variety which here the variable is this one of these minors.
Okay.
Okay?
So
It's a variable in the sense that it's a function. So its values vary depending on where you evaluate it.
So in the current context, it corresponds to a subset of these indices.
It's labeled by a subset, but it's, yeah, I want to think about the actual algebraic objects. Okay? So the guys in the middle are called cluster variables, and they form a cluster. And the guys on the outside are called frozen variables, and when you throw them together with the cluster variables, they form something called an extended cluster. Okay, so now let's see what happens when we change the arrangement. So we'll look at a particular triangle here, this one. This is a triangle, right? Formed by 3 pseudo lines, and we push we flip that triangle. We push one of the pseudo lines, namely this one, through the intersection of the other two, and we get this arrangement. Okay? So what happens is that this cluster variable delta 2 got replaced by this one delta 1 3. Right? Everybody else stays the same. Because even though the topology changed, but for all other regions, the set of lines passing below or above didn't change. So this is called a flip. Any two pseudo-line arrangements are related by flips. This is an instance of the Tit's lemma for Coxeter groups of type A. So what next? Well, let's see how the corresponding chamber minors are related. So this is now something beautiful happens. So when you flip a triangle, go from E to F, these surrounding guys A, B, C, and D stays the same. It turns out that you always have this identity. EF equals AC plus BD. Okay, so this is some exercise in linear algebra. Let's go back. So you have an arrangement of pseudo lines with like 100 lines, and somewhere in the middle there is a triangle, and surrounding that triangle there are some other chambers, and there are these minors indexed by lots of subscripts. So each of them is a minor as a generic matrix. And those minors, together with the minor that you will put in when you flip your triangle, they will always satisfy this identity. Okay? So it's not hard to prove, but it's kind of elegant. Okay, this is actually a special case of these Plücke relations that I alluded to earlier. So this means that if we denoted these guys A, B, C, D, E, then this fellow F, which we place instead of E, which replaced E, is just equal to AC plus BD divided by E, right? So, and then we can keep going. So each time we are flipping, we can calculate the value of the new chamber minor as this kind of rational expression in terms of the other 5 guys. And notice that these rational expressions are subtraction free. There is no minus sign here. So this means if the original guys were positive numbers, or rather evaluated at a given matrix as positive numbers, then everything that you are going to obtain by iterating this process is going to be positive. So what is going to happen is that these rational expressions will be fed into some other rational expressions and some other and so forth. So this will be an iterated rational map, right? Because next time you flip, D,
not the same map. It's
not the composition of maps, all of which look like this. So you have like, some large number, a million of these chamber minors, right? And you fix all of them, and one of them is replaced by product of 2 plus product of 2 divided by the 5th. And now you get a new one. And then you pick another one, and you do the same to it. And as you iterate, these rational expressions become humongous. They become very, very, very big. And they are like multi-layered rational expressions, but there are no minus signs there. So if the original stuff was positive, then whatever you get is positive. And since you can get from any pseudo-line arrangement to any other pseudo-line arrangement, it means that, and any minor appears in some pseudo-line arrangement. It's easy to draw the lines so that your favorite collection of lines passes below some chamber, right? At that point, at a certain point. It follows that if the chamber minors for a given arrangement evaluate positively at a given matrix, then all chamber minors evaluate positively at that matrix, which means it is TP.
So which ones are the ones that you have to check?
The chamber minors of any of your favorite pseudo-line arrangement. And there are like n choose 2 of them, roughly speaking, because there are n choose 2 intersection points, well, plus a little stuff at the edges. So it's a quadratic number in n.
So you just fix a given pseudo-line arrangement and use.
You fix the pseudo-line arrangement, write down those chambers which are indexed by those sets, and that's your criterion, an efficient total positivity criterion. It's enough to check those minors. If they are positive, then all chamber minors are positive because they are, in fact, can be expressed as subtraction-free rational expressions in those chamber minors, right? So
what I wanted to, there's no canonical set of chamber minors which are
no,
considered.
there is not. Although you can canonize a particular, pseudo-line arrangement, right? And then, yeah, okay. And actually, there is a similar game for ordinary classical notion of total positivity. So you can. You can.
But there is a canonical.
No. Again, some people would call it canonical, but Bourbaki would not. So it's not. There is some choice that is easy to state, but it's not. It's not canonical. Okay. So now this example illustrates the main features of a general cluster algebra setup. So we have a family of generators of our ring, which in this case are these flag minors. They satisfy some identities, these relations, right? There is a finite subset of frozen generators among them. The remaining generators are grouped into overlapping clusters. So each cluster consists, in this example, of the chamber minors of the bounded chambers, the ones that can change. These clusters overlap, and they are related by local moves of sorts, which we call mutations, where you remove one cluster variable and replace it by another. And there are certain exchange relations associated with these exchanges, which can be written using the combinatorial data that accompany each cluster. So each cluster is not just a collection of generators of your algebra. It comes with some combinatorial sort of side dish, right? It's not just a bunch of functions. There is also this arrangement which you need to carry with it, because otherwise you won't know how to write your exchange relations. And there is a certain rule for how that accompanying combinatorial information changes in the process of mutations. Okay? But that rule, of course, in this example is very specific to the particular example, right? The Y pseudo-line arrangement, So it looks like not part of a general theory, but something very, very, custom-made just to fit this particular example. And what I'm going to explain now is that, no, it is part of a much more general setup. Before I do that, let me mention that I lied to you slightly on the previous slide, although in the written form, I didn't actually say any lies, but I wrote something. When I said there that you can pick any of your cluster variables and exchange it for a new one and get a new cluster, blah, blah, blah. Because for pseudo-line arrangements, not every cluster variable can be flipped. Only those which are written into triangular chambers. And of course, you can make some mutations, make some flips, and then, like for example, delta 2, 3 now is in a triangular chamber, used to be in a quadrilateral one. So now we can flip delta to 3, but not before, right? Whereas this cluster, general cluster setup suggests, and indeed that's how it works, that each element of any cluster can be flipped. But how? So we don't know. So actually, there are 8 different pseudo-line arrangements for 4x4 matrices, for four pseudo-lines. Sorry, and they are connected by these flips, which actually form an octagon. And for each of them, there are 2 triangular chambers, which correspond to some mutations or flips. And then there is 1 quadrilateral chamber, which you cannot flip. So what should we do there? I mean, even this single example, motivating example that I showed you, doesn't actually exhibit the features that I claim to be present in the general theory. Okay, so let me explain that. Now, in order to do that, we need to translate everything into a universal combinatorial language of quivers. So a quiver, this is an example of people speaking different languages in different parts of mathematics. A quiver is just a directed graph. So for some reason, historically, in some part of the world, namely among people who studied representation theory of finite dimensional algebras, they invented this word, quiver. Actually, this was invented by Gelfand and Ponomarev, and maybe Osip Bernstein also. But anyhow, they came up with this word, quiver, and they didn't know much combinatorics. Well, they knew a lot of other mathematics. And so somehow it stuck. So people in that part of the world use this word. And it's the same as a directed graph, but it comes with a different mindset. So you are thinking differently about it, even though it is just a directed graph. Okay. And there are some technical conditions. You allow multiple edges, oriented cycles of lengths 2 are not allowed, loops are not allowed. So a quiver in this context should be viewed as this general combinatorial data accompanying a cluster. So in other words, I'm going to encode a pseudo-line arrangement by a directed graph, which from now on I will call quiver. I hope you excuse me, because that's the tradition. So, and the vertices of the quiver are going to correspond to the chambers in that example. And some of them will be frozen, some of them will be mutable. Okay, but in general, for any quiver, there is a notion. Yes?
So the quiver also comes with information of which vertices
right.
are frozen and which
That's right, yeah. So the vertices, well, in general, quivers don't, but in the context of cluster theory, yes. So the vertices are colored in 2 colors, frozen and mutable. And so quivers can be mutated. There is a very simple rule, which is described here on the screen, for how to mutate a quiver. So you are given a directed graph. You pick your favorite vertex, mutable vertex, and then you do something to the edges. Namely, you take all directed paths of length 2 that pass through that vertex z, and you introduce a new edge, x goes to y, like by transitivity if you want, but only going through z. So z is your favorite vertex at which you mutate. And then you reverse the direction of all edges incident to z, and then you remove all oriented to cycles. And so at the end of these 3 steps, you get a new quiver. And if you mutate it again at the same vertex, you get back the original quiver. That's easy to check. But what's interesting is that you can play this game and mutate at this vertex and then in this and then in this. This is some kind of game. You can even play it probabilistically if you want. So you start with your favorite oriented graph, and then you click. In fact, when I say click, I literally mean it, because there are Java applets on the web. You can just do a Google search, and you can create your favorite graph very quickly, and then you will literally click on these vertices, and the graph will change. It will sort of change in the vicinity of z, of course, right? But these graphs will quickly become very complicated, like almost complete, and so vicinity of z is really everything, unless your graph is carefully chosen, in which case it will stay manageable. Okay, and so there is a rule which I'm not telling you, but it exists. Okay, it's a very precise and simple combinatorial rule that enables one to associate a quiver with a given pseudo-line arrangement. Just some simple rule. Basically, I don't know, you look around this chamber and you connect this guy with some of the neighboring guys, and you orient the edges according to some, protocol. So it's very, very elementary and simple. I just don't have time to explain it. What's important is that when you do a flip in a pseudo-line arrangement, your quiver changes according to this quiver mutation rule. So it's just a different language. As Giancarlo Roda would say, these quivers are cryptomorphic to these pseudo-line arrangements. So it's just the same stuff, only in different language. But now, of course, we can see, quivers can be much more general than the ones that are associated with pseudo-line arrangements. And then it turns out, luckily, that you can write these exchange relations very easily in the language of these quivers. So these EF equals AC plus BD actually is written in this very, very simple form. So when you flip Z and you put Z prime in its place, what you get is the sum of two monomials, one of which is a product of variables at the vertices from which an arrow points to Z, and another is a product of variables at the vertices to which an arrow points from Z. It's a very, very simple rule. And so then you generalize. Now you can write the axioms, right? So you start with your favorite oriented graph, call it a quiver, put variables by variables now I mean indeterminates, like X, Y, Z, A, B, C, and so forth. And then you start playing this game. Not only do you click and change the graph, but you also change those variables by a rational rule, which comes from this rule, right? So the quiver keeps changing. That quiver carries the combinatorial information that accompanies your set of rational functions. And the quiver changes by the mutation rules. The functions change by this rule, which is encoded by those quivers. Are we clear? Okay, good. And so you can iterate this. You can start with a quiver and just a bunch of variables, and then there is an infinite regular tree of possibilities, right? Because you can click on each of the vertices and mutate that particular cluster variable. But some vertices are frozen, so you cannot mutate those, and those variables stay put. They are sort of in the ground ring of your algebra. So they're not going anywhere, but the rest keep changing, and there is this infinite tree of possibilities. And then you just take all these rational functions that you generated by this iterative process. There will be infinitely many of them, and you just pull them together, and you just take the ring that they generate inside the field of rational functions, and you call it your cluster algebra. Okay, so now you know the definition. So this is a horrible, horrible object, of course, because it's not finitely generated on the surface of it, face of it, right? And you don't even know who the generators are because it's an infinite process, and so it's just totally unmanageable object, so it seems. But that's a definition. Okay, so.
In the example you gave, it was finitely generated, right?
Yeah, in fact, in all examples that people care about, it ends up being finitely generated for reasons that are sometimes mysterious, sometimes clear, in many cases proved.
Maybe that's why they care about it.
Yeah. Okay. So for example, if you go back to that picture that I showed you with these missing mutations, and you just apply the quiver mutation rule to get some new cluster, that cluster doesn't correspond to any pseudo-line arrangement. It's like a phantom object. But we know which quiver is there, and we know which rational functions should be sitting there, and we can further iterate and so forth. And so now something magic happens. We don't get infinitely many things. We recover back some of the stuff that we already had, and in fact, it's just finite. So we just get a finite regular graph. So it's like, it's like the Cayley graph of a group that, because of some relations, collapses to a Cayley graph of a finite quotient group, right? So here something similar happens. So there are some built-in relations between these clusters that somehow make everything, in this example, collapse to a finite object. And we discover along the way one new cluster variable, this omega, written at the bottom. So this is an infinite chamber surround. So okay, so what's the convention here? At this vertex, for example, we have a cluster consisting of delta 3, delta 1, 3, and delta 1, 3, 4. That's a regular sort of pseudo-line arrangement type thing. But this guy, for example, is one of these new phantom objects. It consists of these two chamber minors, and then delta 1, 3 we flipped. That was a forbidden flip. It was a quadrilateral flip. And when you still go ahead and perform it, you get this cluster, which consists of delta 3, delta 1, 3, 4, and this omega guy, which is not a minor, but still, it's a regular function. And then if you continue flipping, you will get this, and so forth. So you only get finitely many objects in that. It's negative sign as right, but it can also be written as rationally as a subtraction-free expression. So this fellow omega can be written as a subtraction-free expression in the deltas, but rational. But when you can also write it as a polynomial, but with a minus sign. Okay. So what do we gain from this? Why should we care? We already understand matrices pretty well. So what do we gain? Well, okay, so in other contexts, we get a sensible notion of positivity where we didn't have it, maybe. But, and also, of course, let me jump to 3. We get some uniform perspective and general tools of this cluster theory, which I didn't tell you about, but hopefully you believe me that there are some general theorems that one can apply whenever one sees such sees these axioms satisfied. And then what's perhaps most important is that we get some candidates for what people would call canonical basis, some additive basis in your ring. So there is a procedure, which in this case is actually quite simple. You take products of powers of elements of a given extended cluster. So for example here, you take any power of delta 3, any power of this, multiply them. Okay? And then you throw in, there are also the frozen guys, which are always fair game. You multiply by some powers of those. And these monomials will all be linearly independent, and they will form a basis of the ring. Okay? And this is not a PBW type basis. This is not like a Gröbner style basis. It's a different type of basis. And in this particular example, it's exactly an instance of so-called dual canonical basis in the sense of quantum group theory.
Did you pick those 3 because they were connected? They were adjacent? Or was there some reason? Or
Did I pick which 3?
Delta 3, delta 1, 3, and delta 1, 2.
Oh, no, just because, no, it doesn't matter which. No. The construction doesn't depend on, there is no distinguished cluster here in this picture. But of course, in order to build this, you need to start with something, right? So
no canonical basis.
Yeah, well,
I mean, you call it.
that's actually true in a deeper sense that you probably expect. Yes, there is no such. Yeah, right. So in this kind of example, there is a canonical basis. Namely, it's canonical because Lustig defined it and called it that way. So now it's canonical. But from a cluster theory perspective, there is not a canonical basis. These products must be part of any. So Lustig also defined something called semi-canonical basis and so on. He sort of felt that there is not really one basis that should be called canonical. So, but anyway, that's the word he used. So let's not get too deep into that area. So I told you that there are some general structural results. So what are they? One of them is the so-called Laurent phenomenon. So remember I was telling you about this iterated rational, these iterated rational maps that we keep plugging in these expressions and so forth. So something magical happens always, no matter which quiver you start with, all these rational functions will actually end up being Laurent polynomials, meaning that the denominator is just a monomial in the original variables. Okay, so this is always true. And this is one of the reasons why here we got a formula like this. So a priori, right, a formula like this might not even exist. But I'm telling you there will always be a formula like this, maybe with some deltas in the denominator. But just a product of deltas, no plus sign or minus sign. These things are actually expected to have non-negative coefficients, but nobody knows how to touch this conjecture. So it has been proved in many special cases, but no. Meaning that even after you cancel numerator and denominator, there will be no minus signs. The reason there is a minus sign there is that we didn't express it in terms of a fixed cluster. Those deltas lie in different clusters. There is another formula, more complicated, with no minus signs. And then another important result of the general theory is the finite type classification. So when does this happen, that when you iterate these maps, iterate this process, everything closes into a finite structure? And this can be completely classified. And guess what? The classification is precisely parallel to the Cartan killing classification. So in other words, these things are classified by Dynkin diagrams, or more precisely, Cartan matrices of finite type. So unordered collections of Dynkin diagrams. So it's the same classification as the classification of crystallographic root systems, finite crystallographic root systems, or complex semi-simple Lie algebras. So in other words, this process is going to produce finitely many objects if and only if the quiver that you started with is a disjoint union of Dynkin diagrams. So it's either a chain or type D, like a fork at the end, and then a chain, or E6, E7, E8, the exceptional ones.
This is a theorem.
It's a theorem, yes. It's a theorem. In fact, we know much more. We know exactly what graph emerges, what is the structure of exchanges that emerges out when it is finite. So for example, in type A, what we get is so-called a sociohedron, which is the graph, this is another instance where flips occur, namely triangulations of a polygon, right? You remove a diagonal and there is a unique other way to stick in another diagonal. And so this graph of flips turns out to be exactly the graph of exchanges in a cluster algebra of type A. So this is a one skeleton of an associahedron, and there is an analog for any type, and there is a beautiful enumerative and algebraic combinatorics of these generalized associahedra associated to arbitrary root systems. I'm not telling you about that at all. Now, what I wanted to tell you instead in the remaining, I don't know how many minutes, maybe -3, or is how, okay, so basically I told you what cluster algebras are and how one thinks about them. What I didn't convince you of is that this is useful, outside the immediate area where this arose. So there is a beautiful example which I sort of left for dessert, where this exactly the same combinatorics arises in a context which is completely unrelated on the face of it, which actually was developed 20 years ago by Bill Thurston with some totally other things in mind. So he developed his theory of laminations on Riemann surfaces and introduced combinatorial tools to study those things. And now it turns out, in retrospect, that these things are exactly cluster mutations, and they describe the dynamics of certain geometric quantities which transform by subtraction-free rational rules exactly as cluster algebra theory dictates. So this is this work with Dylan Thurston that I did and Michael Shapira, and I wanted to tell you about it, but I don't know. It's like 5 slides, but we yeah. Or maybe we should take a break so that anybody who wants to leave can. Well, but I don't know. It's like 10 minutes, so I don't know.
All right, well,
I can turn my back and let everybody leave who wants to leave, and then and then turn around.
Okay, so why don't we thank Sergei and then
Ask a question.
Then anyone who wants to stay longer can stay for that.
Yeah? Nobody's brave enough. So, this game that I showed you on the previous slide, flipping diagonals in a polygon, can be played on any Riemann surface with boundary, more or less. So you start, you take your favorite Riemann surface, just a handle body, and you take scissors and cut out some disks from it. So now it has boundary. Then you take your permanent marker and put some marked points on your surface, including some on each piece of the boundary, at least one. Okay. Now your surface can be triangulated using those marked points as the vertices of a triangulation. Okay. So this is an example where your original surface was just a sphere. You cut out a disk, one disk, so now you have one disk remaining. And on the boundary of that disk, you put 3 marked points. This makes this disk into a triangle, because everything is up to, homeomorphism. And you also marked 1 point in the interior of the triangle, so you have a once punctured triangle. And then you can triangulate it in 10 possible ways. Notice that these are kind of funny triangulations, right? This triangle inside is self-folded. You glued 2 of its sides to each other. But it's okay. It's a triangulation. Maybe it's not kosher, but it's still a triangulation. So, and you see, these triangulations are related by flips. You take this arc in a triangulation, and you can replace it by the unique other diagonal in the quadrilateral, which is formed when you remove that arc. Right? Except when you take this kind of self-folded triangle, if you remove the interior edge here, then there is no way to flip it. There is only right? You cannot stick in something else. Okay, so that's exactly the equivalent of that example that I showed you before, where we had completely other kind of combinatorial dynamics, these flips or other moves, local moves for pseudo-line arrangements, where some moves can be made and some moves cannot. Right? Some chambers could be flipped, some couldn't, and here it's the same. Right? You remove one object, stick in another, but not each object can be removed. And sure enough, if you just believe in the doctrine that cluster algebras somehow must be lurking behind this, then you think about, oh, how do I associate a quiver to a triangulation? How do I encode this combinatorial object using this universal language? And there is a very simple rule. You come up with it pretty quickly. That, for each triangle, you put some, this red stuff is this quiver. You put an oriented cycle, 3 cycle inside it. And here we don't do this because this is on the side of the surface, on the boundary. So those vertices are not used. Anyway, there is a recipe. Don't worry about it. I'm in a hurry. And these things change according to the general mutation rule that I told you when I perform a flip in a triangulation. So they exactly operate as one expects. And even better, right? Because now we can mutate in places where we couldn't before. Now, there is a dual object to the notion of a triangulation called lamination. Here I'm dealing with integral laminations. So integral lamination is a collection of curves on the surface, again up to isotopy. And these curves are sort of, transversal to the arcs of the triangulation. So they start at non-marked points and end at unmarked points, or they can be closed curves, or they can also spiral into punctures. Okay, so basically it's like the correspondence between geodesics and orocycles. Okay, now we, not we, but Thurston actually proved a beautiful theorem that each such lamination can be coordinatized. There is a combinatorial rule that, given a triangulation and a lamination, assigns a bunch of integers to, one integer per arc of your triangulation. And these integers completely, the way they are defined is completely combinatorial. And they determine the lamination. And this is a bijection between z to the n, where n is the number of these integers, and the set of integral laminations. So it's a one-to-one correspondence. So these are truly coordinates. So laminations are like integer points in some, can be thought of as integer points in some affine space. Now, it turns out that we can associate an extra vertex in our quiver, a frozen vertex now, to each of these, to a lamination. And then when we perform a flip, then the rule by which these shear coordinates introduced by Thurston change is precisely the quiver mutation rule. So not only the mutable part, so the mutable part of the quiver is just determined by the triangulation, but the frozen part of the quiver is determined by the lamination. And the edges that can connect frozen to mutable vertices, they are, the multiplicities of them are these shear coordinates, and they change precisely according to the quiver mutation. Okay, so just another situation where some natural numbers, natural in the sense, naturally defined natural integer numbers, change according to these rules. So what does this buy us? This enables us to build models for cluster algebras that arise in other contexts using these triangulated surfaces. because this gives you a sort of global view of a particular cluster algebra, complete with its frozen and mutable variables in the language of combinatorial topology. So, for example, in the type A example that I showed you before, I mentioned that the variables themselves, they correspond to diagonals in a polygon, and then when you flip a diagonal, that variable mutates and so forth. But I didn't tell you anything about the frozen part. So in order to describe a more general cluster algebra, which has frozen variables, and most of them do, you have to also throw in some laminations, and then in terms of them, and using these shear coordinates of Thurston's, you can write down explicitly in a uniform global way the exchange relations that they satisfy. So in particular, this example, my running example, is described by this picture, a hexagon with 6 one-curve laminations, which contains in itself all information about this cluster algebra. So in other words, you don't need to mutate. You don't need this recursive algorithm in order to write a particular exchange relation, right? So the main drawback of the original definition is that you are given information about a small piece of this large picture, right? And then you sort of do like analytic continuation. You extend and extend and extend, and then you reach some distant corner, and only then you know which equations those guys satisfy. Here I am telling you the global picture, which tells you everything about what those variables are, which relations they satisfy, and so forth, in a uniform language. Of course, the problem here is that, well, not in this example because this is finite type, but in general, is that you are going to get infinitely many objects. But we know what these objects are. They are arcs on this surface. So if you have a surface of high genus, of course you can have an arc that goes around a handle, this handle and then that handle and then this. So there are infinitely many of them. But still, you have an overall grasp of what these guys are. You know which clusters they form, namely they correspond to triangulations of your surface by these arcs. And you know how they mutate into each other by these flips, and and there is a general rule using shear coordinates to write exchange relations for any given exchange. So in a sense, you have a global picture, even though it is extremely complicated. Of course, geometric group theory tells you, that awful things can happen. This process can be, doesn't have to collapse at all. I mean, it can give you like an infinite tree with no identification, but still you will know what happens. You have a language at least to describe these things. And then you can classify these algebras, for example, according to the speed of growth. So even if it's infinite, you wonder, does it explode polynomially or exponentially? And things like Tit's alternative for mapping class groups tell you, when exactly it is polynomial, when it's exponential, and so forth. So I'm just dropping some names. That's all I have time to say. Thank you.